Okay, good morning. I want to record this just so we can get back on track. I know it doesn't seem like we've gotten behind really a whole bunch. We kind of are. But we also have Labor Day next Monday, and we're going to be missing out there. So I might be recording a few of these over the next few days and posting them. So, first of all, we're going to be doing one-dimensional vertical motion, and then we'll be looking at independence of perpendicular motion, or just the independence of perpendicular, meaning x and y or x, y, and z, vectors. Okay, so all of them in general. Vectors are, when you're perpendicular, they're orthogonal, they say. Perpendicular and orthogonal are the same thing. They don't have effects on the other dimension. Okay, so they just simply don't affect the other motion. You have to break it down into components and then treat them independently. So we're going to talk about that, which leads us to projectile motion. Okay, so what I normally would do is I would have you guys go through, and we end up talking about, I have a group project normally that we do. It's a problem, and then I have you guys kind of work together on it. But I'm going to be doing it independently. Excuse me. We'll be doing enough working together, with the labs and everything. So, okay. So here's the problem. A person flips a coin. So at a football game or a basketball game or whatever, you've got the rep flipping a coin. Here's the thing. They flip the coin, straight up into the air. Okay, so I don't know. Let's put our person here, and their other arm's just kind of hanging down here, doing a whole lot of nothing. They flip the coin straight up into the air, and it goes up to a certain point, and it actually comes back down and hits their hand at the exact same height. Okay, so it will hit their hand at the same height as it lands. Okay, and the initial velocity is, let's make it, I'm gonna reduce it from what I normally do. Let's reduce it. Let's make the initial velocity v naught equals 4.5 meters per second. Okay, so we've got a couple of questions. We want to know A, how high does it go? And B, how long is it in the air total? Okay, how high does it go? Well, that's length, right? In the y direction. How long is it in the air? That's time. So let's let's tackle A first. Okay, so let's tackle A. Hopefully, we're given this. Okay, so hopefully we can figure out that at the top, okay, so down here's V naught, up here is V final. What is V final? If it's at the top and it's not moving left or right, it's only going up and down, it actually stops at that point. So V final equals 0. So we know V initial, we know G, which is our acceleration. We know that we're asked for how high does it go. So we're asked for delta y. Or you could say that delta y equals h for height, whatever you want. Okay, delta y is nice and easy because we have these things. We don't have time. If you don't have time in your one of the givens or what you're asked for, then the chances are this is the equation that you want to use. And I'm going to put G H. Let's do delta y. Let's do delta y. Okay, now all I have to do is define what's up and what's down. I'm going to define up. I can't put my hand down on the board, so let's do up as positive and down as negative. So if up is positive and down is negative, what do I got to do? I've got to change this sign so that we reflect the fact that G points down. And if the distance was also down, I'd have this negative and this negative, and which would make a positive. Okay, but it's not. The up is up, positive, and a positive times a negative is a negative. So what is that going to give us? We just need to do a little algebra. So there's algebra involved to get this alone, right? We want that alone. So how do we do that? We've got, I'll do a couple of steps. 2g delta y, when I move this whole term to the other side of the equation, I'm going to move the v final with the v initial to the other side of the equation. And now I'm going to divide through by 2g. So all right, hopefully that works for everyone. And that's the equation that we're going to be using. So I'm going to box it in. That's our equation. We know V naught. What was it? 4.5. Excuse me. So we also know V final is 0. So what we're really left with is delta y is equal to 4.5 squared meters squared per second squared. And we're going to divide out by 2 times 9.8 meters per second squared. Okay. I honestly have not done these since I changed the numbers. I haven't done the calculation, and I don't know what 4.5 squared is. Should be less than 25, but more than 16. So let's see here, 20.25. So I've got 20.25 in the bottom, meters squared per second squared. And I've got, that's 2 times 19 plus 1.6. So that should be 19.6. And that's meters per second squared. Now we did it in class. This and this end up giving us nothing but our meters squared. The meters total. So I can cross this out and cross that out, and we're left with nothing but meters, and that's what we need. So 20.25 divided by 19.6 divide there, 1.033. So 1.03. The 3 isn't going to let us round up, so we'll just say 1.03 meters. So it doesn't go up very high, okay? And that is our height. It's a positive height, so we did our numbers correctly. Everything was done correctly there. And now let's go on to B. What is B? Let's go back and remember what was B. How long is it in the air? Okay, what is the time that it's in the air? So I'm going to write total time in air. Okay, between the time that's thrown and the time that it's caught. So now we know the height. We know the initial velocity. We know the final velocity. We've got all kinds of stuff. So we can probably use an equation, v final equals v initial minus g, because it's pointing down, times our time. And then all we have to do is a little work. Now, there's two ways to do this, okay? So let's have our, now I'm going to draw it so that we can see that it goes up and comes down, okay? And we can cut this thing in half, and we can figure out the time from V naught to V top. Let's call it V top, okay? We can do that. And then we can multiply by 2. Okay, whatever our answer is, we should be able to multiply by 2. Why? Because there's symmetry in the problem. We have symmetry. Everybody loves symmetry, and you can exploit it to get your great answer, and that makes things quite easy. It's just 2 steps, all right? Because in the end, you're going to multiply by 2. Well, or we can say that V initial is pointing up, and because of symmetry, it will be minus V initial when it comes back to hit his hand. That would be our V final right here. So we could do that as well and put it all into one equation. We don't have to deal with the 2 anymore. And that will work as well. And most people would do it the other direction. I'm going to do it this time. I'm going to do it this way. Okay, we're going to use these guys this time. So just to show you, this is how it works. We're going to put our minus V naught here. We're going to say that that equals our positive V naught, and then we're going to be dividing out, or I'm sorry, doing this algebra. Okay, so this is the equation that we're going to work with, and then we don't have to do the 2 times, okay, because we're going V naught and minus V naught. And this should work. Okay, so let's do it. Let's put GT on the positive side, and we'll have V naught plus V naught. And then I'm going to divide everything by G, so we get our G back here. Okay, did you guys see what happened there? All right, good. So now we've got our V naught. Well, guess what? This is where our 2 comes into, because V naught plus V naught is just 2 V naught, and we've got this. And now our time is nothing but 2 times V naught over G. And our V naught was 4.5 meters per second. We've got G at 9.8 meters per second squared. And this is, oh wait, gotta have a 2 in there. We're gonna multiply that by 2. And let's figure out what our time is. Okay, our time, okay, 4.5, 9.8, we're going to divide that, and then we're going to multiply by 2 times, and then that gives us 0.918. Now the next digit's a 3. We're not going to round up with a 3, so we can say 0.918 seconds. And that is our answer to 3 significant figures. Now, let's see, what were we given? We were given 4.5. So we're really given 2 significant figures. So we can come and change that to the correct significant figures of 0.92 seconds. And that's really our answer, and we can scratch this guy off as our answer. That's our leading up to answer. Sweet. So hopefully that went well for you. Okay. Now, let's talk a little bit about our independence in X and Y. So if you're walking in a city, we've got city blocks. I'm going to draw little small city blocks here. And I need, what, 8, 9 of them? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, hopefully those are relatively similar blocks. And we're going to go up 1, 2, 3, 4, 5 blocks. So we start here. We're in some, who knows, some downtown. Typically these are downtown situations. And we're going to go here. Okay, that's where we need to go. Now, if we were able to go straight there, that would be nice. We would have some vector C. Okay, that would be a nice way to go, but we can't go that direction. We have to do some combination of 9 blocks in the east-west direction. We could call it east, or we could say that equals our positive X. That's fine. And we could say this is north, or positive Y. Okay. So let's see. Here's our 1, there's our 2, there's our 3, and there's our 4. All right. Again, excuse me. I'm so sorry. I don't know this cough. Okay. It's not really a cough. I don't know what I got going on. Okay, this is 5 blocks going up. And that's a 5. So, all right. Okay, what is C? Let's figure out what C is. If we were able to go that direction, we'd have C is equal to 5 squared plus 9 squared square root. C is equal to 25 plus 81 square root. and 1 and 5 is 6, 8 and 2, that's 106, so we're going to take the square root of 106, and this is blocks, by the way. Squared blocks, squared blocks, squared blocks, squared blocks, but you take the square root of blocks and you end up with block. Squared blocks gives us blocks. Okay, so we'll have whatever square root of 106 is. Let's do it. 106, enter, and then we're going to take the square root of that. 10.295. Let's do 10.3. And we'll say C is equal to 10.3 blocks. Okay, that's one thing, all right? What we've done is just the Pythagorean theorem. You guys are good with that. And so fine. But the reason we're looking at this is to talk about the independence of these two things, okay? And really, you could walk over 2, up 1, and just keep going like this, right? I don't know, maybe we go up 2, and then we go over 1, and then we go, I don't know, maybe we go over 3, and we go up 1, and we go over 2 more, and we go up 1, and then we go here, and then we go up the last one. Okay? That's a legit way to go, but we are forced to do that because the streets run that way and the buildings don't allow us to go in between. I mean, let's just forget about alleys and that kind of stuff. Everybody's wanting to go down the alleys. I don't know why. Okay, all right. So we do this on the streets. We've walked on the sidewalk. We're in New York City and we don't get mugged. Everything's great. Okay, I'm sorry. Don't be afraid of New York City. It's a wonderful place. I'm just kidding about. You don't get mugged. All right, most of the time. So, as you can see, these motions are independent, okay? There's nothing to these motions. There's no way that we can go without them being independent, okay? We are forced to either go up or to the side, horizontally or vertically. There's no other way to do it. Well, it turns out that that is pretty much real life. All the things that happen in the y direction, none of it pertains to the x direction. Okay, so what is our total? What's our total distance traveled? We did 9 blocks. And we have to add 5 blocks. So our total distance is 14 blocks. Okay? So that's our total. Okay, this is equal to the total distance. I'll just call it TD. All right? So this is a simple way to think about it. Now, in real life, you don't have to. In real life, you can take this path C a lot of the times, right? Or we're going to add 2 vectors. We're going to add the vector that goes to the right, A, and we're going to add that vector B to it. And we'll get this vector in the middle that's really the vector that we have, and there will be a theta involved, and we'll end up with the absolute value of C equals 10.3. And then we'll figure out what theta is. Theta is going to be the arctangent of 5/9. Okay, I don't know what that is. I didn't figure it out. You guys can do that. But the point is, it's independent. You only went 5 blocks north. You only went 9 blocks to the right. These are independent things. So now let's talk a little bit about, here, let's, this is our C vector. All right. A vector has to have a magnitude, that's our magnitude, and a direction. Let's just finish it off. 5, enter, 9, divide, arctangent, 29 degrees. Okay, so theta equals 29 degrees. All right. What about the famous one? Oh, there's all kinds of famous ones I get. I like using the baseball player, but there's archery, there's anything you want. You initially start out at your projectile's origin. If it's baseball, it's about 1 meter off the ground, maybe, half a meter to 1 meter off the ground. They hit that with the ball. The bat. They hit the ball with the bat, and it does something like this. Yeah, not terrible. All right. There's an initial velocity that it has. Okay. The velocities at each step along the way are tangent to the curve. So these are just velocity vectors. So I could call this, we could call this point 1, point 2, and point 3. We could even have a point 4 down here at the end. And this is V1, and it's a vector. That's a vector. V2 vector, and V3 is a vector. Those are the velocity vectors, but there's also a positional vector. So this is R1, the radius from the origin. There's R2. There's R3. And then lastly, we've got R4, but R4 also equals our range. It's the distance that when it comes back down at this point here, at the final point, when it comes back down at the exact equal height that it took off at, when you find that distance, that is what we call your range. So there's these different vectors. Okay, we've got our positive vectors. All of them are positive. In this situation, of course, it could drop down, and we'll have negative aspects to the range, to the positional vectors. These are positional vectors. So positional are RI vectors. Velocity vectors those are VI. Okay, now we have, let's take V1 for example. It's got an X component, V1X, and it also has V1y going up. V2 has a slight drop. Okay, so V2y is slightly negative. Okay, V1x still the same, right? Why is V1x the same throughout? Because V0x, there's no acceleration in the x direction. What's the acceleration in the x direction? Ax equals 0. So when you initially start off with V0x, it's not going to change. You will always have V0x at every single point along the way. Okay? The only thing that's going to change is initially we've got a big up here for our velocity. Our V0y is big, going up, and then gradually our V0y is going to be going, or our V4y is going to be going down. Just like before when we threw the coin up in the air, these are going to be equal, okay, and opposite. Why did I, yeah. I don't like the negative sign. Our vector happens to be negative V0y. All right, it's definitely pointing down, we know that. So whenever we do our, whatever calculations we'll do with V4y, we're gonna have to make it negative, okay? We gotta have this negative sign in there, one way or the other. So that's how it works. So we can then, we'll just give ourselves a little room here. So we've got our x direction equations. We've got Vx is constant, and that's V0x. Why is it constant? Because there is no acceleration. So our x final is equal to our x initial plus V0x t. Okay, and we'll gradually get a larger x final because we've got this velocity taking us all the way to our complete range. In the y direction, we have Vy is equal to V0y minus gt. Okay, because we've defined positive x to the right and positive y going up. So let's get rid of my... Okay. All right, what about our position? Our position is going to be y is equal to y0, whatever we started with, which we're going to say is 0. Okay, 0. And we're going to be adding V0y times t minus 1/2 gt squared. The minus sign comes from the fact that g points down. This is not always 0. It happens to be 0 in our case, but sometimes it's going to start with a certain height. Okay, so it may start with some height and it's not always 0. The other equation that we have is our V final squared is equal to our V initial squared, and minus our 2g delta y. If we're looking at point 2, if we're looking at this point here, then our V final would be V 2, okay? That's our velocity at 2. So it all depends on where you're looking, right? It's not necessarily at the very end. It depends on what it is that you're looking for. So we can, maybe a good idea would be to eliminate that VF and just say V squared equals V naught. And this is the one we don't know where that is, because it could be any of them, okay? So it could be anywhere along the path. In fact, it could be the top. It could be anywhere. So it just so happens to be the one we're looking for. Okay, hopefully that was pretty clear. Let's draw a picture again. Well, we could probably use the same picture. Let's label one other thing. I'm going to say that this is halfway. So symmetry goes our half range to here. And this is our top. So we'd have V top is simply, there's no Vy because Vy is 0. So V top has to be V naught X completely. All right. Okay. Sometimes I derive stuff, sometimes I don't. I'm going to not derive this equation. Our position at any point, oh boy, that didn't work. Let's redraw this thing. And we'll just draw it a little sharper. And we don't need all this out here. We'll label our X and Y. And that's not a very good parabola, but let's see. It's not as easy as it looks, folks. I need a dot matrix printer. All right. So here's our top. Here's our position, our top vector, our positional vector. And this is also, this distance here is our Y max. So our max height, you can talk about it any way you want, but that's our Y max. Okay, what else do we have? We've got our range. Okay, we've got half range to the middle. Now this could keep coming down like so, and we could have been asked for this position, our final, if we want, or we could call it like position 5 and change that final to a 5. We could do that. I just want you to know that this is doable, okay? And that's our 5 vector, okay? These things are definitely doable. So let me give you an equation for the position, we're talking about our position, so let's do our top. That's going to be, this is half range to our, in our x direction, and so we know that y max squared plus 1/2 range squared, if we take the square root, that's our position. But in general, what does that mean? In general, we can say that r, the r vector, is equal to our x squared plus our y squared. Take the square root. And then, of course, theta is equal to the arctangent of y over x. Now that's always, here, let's draw theta. When you put the x in the denominator, that is with respect to x-axis, okay? So whatever's in the denominator gives you the respect with respect to the that axis. So if we had this switched around, x on top, y on the bottom, then we'd be doing with respect to the y-axis. So keep that in mind when you're doing your angles. And either way is fine. I don't mind, as long as you just define that I'm not doing theta, I'm doing phi instead. Something of that nature, okay? Or label it, all right? Okay, so there's our position. Now let's do our velocity. We're going to have to do that independently. So our net velocity at any point is going to be Vx squared plus Vy squared at any point. But we already know that Vx is always going to be V naught x. So whatever we figure out there, we can figure out what V naught x is. That's always going to be the case. So I can even put a little V naught there, V naught x. The Vy definitely changes at different points, right? So this could be my Vy at that point. Cool. And then, of course, theta. And we could call it theta v if you want. So we've got our theta v. That's our vector right there. And this is our theta v. Okay, for that point. So theta v, again, arctangent of Vy at that point over V naught x, because it never changes. And this will give us, with respect to the x-axis. And it's actually with respect to the positive x-axis. Okay. So, all right. We've got all kinds of things that we've been given. Now we have to figure out how we can do these things. So let's do a quick example. And then we've got a group problem that we can work with later. Let's see. I'm going to do the group problem in the next video. So let's just quickly do let's just quickly do our problem. If I can do anything quickly. We'll see. We've got a stunt person. The stunt person is riding their motorcycle, and this is their trajectory because they're riding their motorcycle off a cliff. Okay, so they're going along, and they ride it off the cliff. Okay? For a movie, we've got Vx, V naught x, is equal to our Vx, which is equal to V in the x direction, but at the beginning, that's our total V. Okay, that's our only V. So we can say V initial, and that is equal to 5.0 meters per second. We want to know, the question is, what is the person's, and when we say this, we're dealing with their center of mass, okay? So we're going to be dealing with the center of mass of the motorcycle and person together. What is the person's position and velocity at t equals 0.25 seconds. So we need to know the position and the velocity. We're going to take it into in two steps, but I'm going to draw. Here's the tangent to the curve at that point. That's their net velocity, their total velocity when we've added both together. Both vectors, this vector and this vector. That'll be our V. And then this is our position here. That's our position vector. So that's how you would want to draw it. That's our situation. Let's move up, give ourselves a little room. Let's go. We've drawn it out. What coordinate are there's quadrants, right, to a system. So we've got quadrant 1, quadrant 2, quadrant 3, and quadrant 4. We're going to be in quadrant 4. Okay? What does that tell us? That means that we've got negative going down and positive going to the right. Okay? And that's the same for both our positional vector and our velocity vector. Let's put a few things up in the corner. Okay? We're going to just kind of we're going to put a little bit of room here up in the corner for things that we know. We know that x naught is equal to y naught, which is equal to 0 because it's at our origin. We've got the velocity mentioned. We know that v naught y is equal to 0. We know that g is negative in our situation. We've defined this to be down, so g is negative, so that's minus 9.8 meters per second squared. And that is our acceleration in the y. And also, our acceleration in the x we know is 0. So all those things we know, we can plug numbers in later. We don't need to do much about that. Where is the motorcycle? So we've got to figure out a couple of things. We've got to figure out this Rx, and we have to figure out Ry. So where is our motorcycle? Let's just say position. And x, simple equation, we're going to go back to the equations that we need to use. Here we go. This equation here is going to give us our position. This equation here is going to give us our y position, and we're going to take the x and y and put them together with Pythagorean. So in the x direction, we've got our v naught x times time. Okay, and it just so happens that we know what v naught x is, so we can do that. What about the y direction? In the y direction, we've got y naught plus v naught y times t minus our 1/2 gt squared. Well, y naught is equal to 0. V naught is equal to 0. So that really leaves us with minus 1/2 gt squared. And we know those numbers, right? We've got all that stuff up in our cloud of knowledge. And so we can go through and figure out both x and y. So x, let's put some numbers in there. 5.0 meters per second. We're going to multiply by 0.25 seconds, and that's going to give us 1.2 meters. In the y direction, we've got, I'm going to divide 9.8 by 2, so we've got 4.9. So we've got minus 4.9 meters per second squared times. Now, t squared, if you square 25, you get 625. Do a little bit of moving your decimals around, and you'll get this. And to make up for the fact that the decimals are moved over 2. And that gives us minus 0.31 meters. Okay, so they didn't get very far in the y direction. They got further in the x direction. That's fine. We're not giving them very much time to go over the cliff, so that's okay. Now we want to know what r is, so we say r is equal to x squared plus y squared square root. And of course, this is our absolute value of r. And we have to square 1.2, and we're going to square 0.31. I'm dropping the negative sign because negative squareds are equal to positives. So it doesn't matter, positive, negative. It's still going to be the same. And we're going to end up with, let's bump all this up a little bit. Our distance is equal to, if you do this, it essentially gives us our 1.2 back. Okay, so rounded and all that, it gives us that. But what is theta r? The theta r, just so you know, is this right here. That's theta r. This is theta v. So theta r, what is theta r? We do the arctangent of y over x. That's going to be the arctangent of 0.31 over 1.2. Now, if anybody's really paying attention closely, they'll notice that I need to put a negative sign there. What is that going to give us? It's going to give us a negative theta r, and that's equal to minus 0.5 degrees. I'm going to delete this negative, okay, because theta r is theta r, but it happens to be negative, and that's true, right? We know that theta r happens to be negative because we're in this quadrant. We're in this quadrant, so it has to be negative with respect to the x-axis. It points down. Okay, what about our velocities? Let's handle our velocity. Let's just remind ourselves the time. Let's remind ourselves the v naught x is equal to 5.0 meters per second. And we can go to Vy is equal to minus, let's put our V naught y is equal to 0 meters per second. V naught y, because V naught y is 0, we're going to just go straight to Vy is equal to minus gt. And we'll plug in some numbers there. Minus 9.8. We're going to end up with meters per second, so I'm just going to say meters per second here at the end. And we're multiplying. That's a multiply. So a quarter of 9.8, and that's going to give us Vy is equal to minus 2.4 meters per second. What about Vx? Well, Vx never changes. It's the nice part about projectile motion. We can just say V naught x is equal to 5 meters per second. What is our V? Well, that's our 5 squared plus 2.4 squared. We're going to take the square root, and then that's going to pop out a meters per second. And what is that equal to? 5.5 meters per second. And that's going to be equal to our absolute value. We still need the direction, our theta v. So let's pop up here, give ourselves a little more room. Theta v is equal to the arc tangent. And our 5 goes in the bottom. Our 2.4 goes in the top. We do have to make it negative, our 2.4. So we're going to end up with a negative, and it's roughly 26 degrees. Okay? So our velocity goes like this. And I've exaggerated the situation because this is more like 45 degrees, but this is our theta v. Okay? And it puts us in the fourth quadrant, means that theta v with respect to the x-axis has to be negative. So then we can just box this in. We've got two things boxed in, and we're done. And that's it for this recording. Thank you for watching, and we'll have another one soon.